Good morning and a warm welcome to everyone to the second seminar in our series, The Inevitable Transition to the Electrical Society. The topic today is energy storage, which is the second in the series, and there will be a third seminar in September 7th on energy efficiency. My name is Göran Andersson, and I'm a member of the Engineering Sciences class of this academy. And I, together with Lars Andersson sitting here and Harry Frank, we have put together the program of these seminars. The purpose of these seminars is to shed light on the various technologies and options for action that are available for the creation of the future energy system, where we believe electricity will be the backbone. Both technical, economic, environmental and social science aspects will be addressed from a Swedish as well as from an international perspective. A couple of weeks ago, we held the first seminar in the series on fossil-free electricity production, and I'm convinced that today's seminar will be as interesting as that one. We have three prominent experts here today that will share their knowledge and experience of three different aspects of energy storage. A special welcome to you, and many thanks that you could take the time and travel here to Stockholm today. We will follow the same format as last time. That means that each speaker will give a 35 minutes presentation, followed by 10 minutes of questions from the audience, and hopefully good answers from the presenters also. A practical reminder, there is an automatic audio recording system in this room. So when you put your questions, you don't need a microphone, but it also means that if you're chatting during the presentations, that will also be recorded. So a plea is that please do not chat too much and too loud during the presentations. Okay, so without further ado, we will now start the seminar with the first presentation with the title Role of Storage in Future Energy Systems, and it will be given by Professor William de Hesseler from Katholieke Universiteit Leuven. Professor de Hesseler has master's degree in electric power engineering and nuclear engineering from University of Leuven, and a PhD in plasma physics from University of Wisconsin in Madison. He worked a couple of years at the Max Planck Institute of Plasma Physics in Munich, and in 1996 he joined the University in Leuven as a full professor in energy conversion. He is the co-founder and currently the director of Leuven Energy Institute, and he's a member of the Belgian Royal Academy of Sciences and Arts. So please, we're looking forward to your presentation.
Good morning, and thank you, Göran, for the introduction. I will have to retire by the end of this academic year, so the 1st of October, but I won't retire, intellectually, that's pretty clear. So I will still be very much interested in following up what is going on with this massive transition, or let's say revolution, in the energy field, especially the electrical energy field and then also the others. And my field of interest basically is energy systems integration, flexibility, and sector coupling, which is basically the new thing where we have to decarbonize the whole overall system. Okay, first this is the overview. I'm not going to read all this, but you will see whenever we come there. And let me first give you some what I consider relevant references. I've tried to give you some modern references because, first of all, it's kind of a challenge to summarize everything in 35 minutes if you used to lecture for 2 hours in a row, okay? And I don't like to work in slogans, so I'm going to try to explain a few things, But then if you want to dig deeper, then please consult the literature. But having said that, and I have mentioned the word consultant, you will actually see that I'm not a real consultant. I do consulting from time to time, but the real consultant will never give you his sources, okay? Well, this is indeed then a massive study that you might have a look at. It started in January 21, and the last thing was published basically 2 months ago. That's from the Renewable Renewable Energy Laboratory in the United States. Yes, indeed, it has 7 volumes. Okay, so if you want to read up to date what is going on, this is indeed then a good reference to start out. But there are other ones. MIT, of course, doesn't want to stay behind. They came out with their Future of Energy Storage last month. And then there are also some interesting things at the back of this document that was released about 6 months ago by the IEA on renewables 2021, and also a projection towards 26. There are also some other interesting things. Schmidt, I'll refer to them a few times, and here you have the references. If you Google them, you can find it then. Some other, especially for long-term and seasonal storage, some interesting recent documents. This is a kind of interesting one that is quite, well, it's 2022, I think, from Runau and Hubert from Germany. I'll just mention a few things of what they're saying, and then, of course, I have to also advertise our own work. This is something that we did on levelized cost of electricity with the original paper there in Energy Economics, but then I'm also showing you on the right-hand side, chapter 6 is a kind of reworked version of that work, which is a little bit open for, let's say, non-experts. Now, why do we need energy storage? At least, why do I think that we need energy storage? Well, clearly it's driven by the electric power system. And we know that electric energy is not easily stored, at least not in large quantities and at affordable prices. And it's always interesting to look and to compare with the food sector, okay? Because you might wonder, okay, how does it work that we have been able to do so well in the food sector? I know that we have some troubles at this moment, but of course that's because there is plenty of storage available there. Cooling houses, refrigerators, these cooling houses, they sometimes stored for several months of food. Water basins, if you want to think about water, etc. None of that is basically easily available in the electric power community. And the situation becomes much, much more critical if you have quite a lot of not well dispatchable, I usually call them naturally fluctuating renewable electrical energy sources. That's why the double E stands there. They're variable and they're not always fully predictable, so they have some kind of stochastic behavior. If you look at this quite famous curve, called duck curve from California, it effectively shows what type of typical profile you're going to have during the day. The curve that you see there is what we call the residual load. It means it's the actual load minus everything that is variable, so solar especially and a bit of wind subtracted. The Americans would call it the net load. Okay, then you see that in the future that, well, they actually projected that in 2012 and you run up to 2020, which is basically already the past, that you have massive ramping consideration that you have to take into account. How are we going to deal with? And indeed, this might be an interesting opportunity then for storage. Now, storage is only one of the flexibility means. And I've just listed them there, and each of them could be considered and should be considered and will be considered, but all to a different degree in different systems. You have cycling of thermal plants. That's especially going to happen with gas turbines, but maybe also others. But we shouldn't use any fossil anymore in the far future. So no more natural gas, unless we do carbon capture and storage in the far future. The grids, it's actually relatively easy. You say, let's just make lots of transmission lines, but do we get them timely, and do we get timely the permits? And maybe if they require that we bury everything underground, it's all DC, etc. And so it might lead to exaggerated costs. Active demand response or active demand participation, as it is sometimes called, will this be sufficient in practice? And then sector coupling. So electrification of the other sectors, especially then mobility and the heating sector, read industry. Yeah, from the electric power sector viewed, it's basically another type of demand management. Curtailment of superfluous PV and wind. Well, that will be needed in order not to over-dimension our system. So we will need it on the one hand, but it should be minimized, not to waste too much energy. And of course, then finally, storage of electrical energy via all these different means. And as I said, we will need all of them, and in a good market design, all these technologies will have to compete, and storage will also have to compete with the others. Now, the question then is, where should we do the balancing and at which level? I've given you two examples. You can do it on the distribution side, so the local side, and you can do it on the overall, the wholesale side. And that's still not fully determined. I guess it will happen on both ways, and we will have to see who are the best winners. Now, just a few quotes. Paul Delholm, who is a little bit the Pope. Oh, I have to be careful because this is not a Catholic country. Well, whatever. So it's of energy storage in Enrel, so in Denver. He says, yeah, but wait a minute. Energy efficiency of storage is 70 to 80%, so you still throw away 20 to 30%, which is de facto also kind of a curtailment. Okay, then Mark Betzüger, sometimes an opinion maker in Germany, he said, well, don't underestimate the demand response if appropriate price signals are present. And indeed, storage should also be able to be used and for a multitude of so-called ancillary services in the electric power system, especially on top of arbitrage. I will explain what arbitrage actually means, and portfolio optimization. Let me first give you some elementary concepts so that you keep that in mind. First of all, I will always use the words here, power and energy in the literal physics sense. So for me, power is the rate of change of energy. I don't want to use the word power as just being synonym of electricity. I even don't like it, but okay, who am I? Okay, so you have the installed power capacity, and that's expressed in units watt, kilowatt, or megawatts. It's basically the charging rate, the discharging rate. It's like a flow, a flux. Then you have the energy capacity, that's the content. If you compare that with the bathtub, it's the amount of water that is in the bathtub. Okay, it's expressed in kilowatt hours or megawatt hours. Now the IEA has come up with a new term, and they call that, instead of capacity, they call that the capability. Okay, fine. I'm also going to use that from time to time. So to make a distinction between when we talk about capacity, it's the power capacity, so mainly, and for storage, it's the discharging capacity mostly, and then you have the energy capacity, that's the amount that is available to be discharged later on. Then you have the number of hours that you can discharge, which is very important. It's basically the ratio of E over P. You have a round-trip efficiency, which usually is split, let's say, in part for charging and for discharging. But it's clear that from this simple expression, the TC stands for charging, D stands for discharging. Clearly, because of that efficiency, if you discharge at nominal power, okay, you will have to charge for a longer time, being equal to the time that you discharge over that efficiency, which is usually then 0.7, 0.8, or even 0.9 sometimes. So just to make these things clear, okay, so you charge power, you discharge power, and you store energy. In some of the documents which are internationally published, I read, even the PhD thesis, okay, I read that people store power. If my students say that, I flunk them. No excuse. They come back in September then, okay? You may like it or dislike it, but that's the way it is. Now, the investment cost, you have to be very, very careful. What is the denominator? Is it the investment cost per unit power capacity or per unit energy capability? And then you have other things. I've just listed them here, but sometimes might come up. The total number of discharge hours per year. the number of cycles per year. You have the state of charge, is it completely full or not, the depth of charge, etc., but they're less important for what I'm going to tell you. Also, just dealing with that a little bit more, is that clearly, if I divide the efficiency equally over the charging and the discharging side, okay, then it means that the amount that you're going to discharge, the amount of energy that you can discharge, will be less than the amount of energy that you have charged. That's because of the efficiency. Okay. Let me then run through a few storage technologies. Of course, as you will see, I will not just look at all of them, because otherwise we will be here for 2 days and it won't be all that interesting. You all know that they're available in those references. Now, electricity itself is pretty difficult to store, because the only real electric energy storage is supercapacitors. That's it. Everything else you have to go and do some energy conversion to a different type of thing. Pumping water, well, it's a very archaic old thing, but I will tell you in a second, I'll show you in a second, don't forget it. It's one of the most important ones, worldwide, and now and in the future even. So it's a mechanical thing. You just pump up water and then you just drop it through a turbine. Electrochemical, batteries, you have flow batteries, you have fuel cells. You have then temporary fuels, hydrogen, methane, hydrogen-derived fuels. You have then magnetic field, the SMES, superconducting magnetic, etc. Mechanical, flywheels, compressed air energy storage, CAES. Sometimes we also talk about virtual storage, etc. and all these things. I'm just going to concentrate on a few of them, just to not explain what is behind it, because there will be a session on, well, there will be a talk on power to gas or power to X. So the hydrogen story, let me say, and also on batteries. So I'll just say a few things. Now, this is from a publication of Energy Technology Perspectives, the IEA 2014. Okay, that's there. Okay, and here you see that they've looked at the different difficult technologies as a function of first on the horizontal axis, the discharge duration, and then the installed discharge capacity, which is in the vertical axis. You have them all there. Typical of them, you see batteries. You see then on the right-hand side there hydrogen, that's for long duration, and then pump hydro storage sits somewhere on the top in the middle. Okay. Now here, this is just for your information. I'm giving you this. You can consult that if you want to. By the way, this document is freely available, downloadable from the web. It's a bit old, but these things are still, I would say, pertinent. This is a different story, especially as you will see. This gives you the investment cost especially. But this will have to be reviewed or updated. That's pretty clear. And let me just show you a few things. This is what has happened, so I won't go too much in detail, because otherwise the person talking about batteries won't like it. But I would just like to give you an idea. So this is a picture I took from there. Look at that decrease over the last decade, which indeed opens up quite a bit for storage. And this is to some extent also the thing behind electric mobility and why indeed battery electric vehicles probably are going to win the game. We'll see about that. This is from that other publication, also very recent, and you see that the tendency, these are the triangles on the left-hand side, also show clearly what that means. If you go then to the bulk system, in other words, wholesale for utility scale battery systems for our lithium-ion, this is what is then, so this is for a system. So the cost for a system is different than for a cell and a pack, etc. With, of course, there's quite a bit of uncertainties. But this is an interesting thing that you might want to consider. And that's why you have to always be very careful when you see then certain plots. I always tell my students, please look at the footnotes first. Okay, then they will tell you, if they're honest enough, what you're actually looking at before you try to figure out what it is. The left-hand side is the installed capital cost per kilowatt hour. So that's the energy capability cost. The right-hand side, that is per unit DC power capacity. And this is for different hours. Okay? Now the tendencies are similar to this, right? But look at the hours, okay? And if I just click then further, then with increasing time duration, this thing goes down as far as energy is concerned, but it goes up as far as power is concerned. And the reason is that when a system, that the energy contents and the power, the discharge power, they don't scale in the same way as by just multiplying this thing, right? For instance, there is an interesting formula down here. You have then the energy components, which is the volume, and you have then the discharge components. The discharge components, for instance, the inverter, doesn't scale too much with the energy content, but it does scale with the power. So you don't have to multiply them by duration in order to convert one into the other. I just wanted to tell you this, be careful when you look at the literature. Now this here is another case where you have to be careful, it comes from that MIT report. On the horizontal axis, it's the energy capability cost, we would call it. On the vertical axis, it's the power capacity cost. You have there on the left-hand side, this is for chemical storage, so small cost in energy capability and high cost for in power. So that's hydrogen, pump hydro storage, these types of things. The lithium-ion batteries would sit down below, and that would be the flow batteries in the middle. Okay, now you look at the Andersson report, and they give a somewhat similar picture where they have drawn a horizontal and a vertical line through the lithium-ion battery thing. That's what you see there. Okay, so on the left-hand side on the top, that's the place where you want to have things for a very long duration. On the right-hand side here below, that's what you want to do for, indeed, and frequently using short-term interventions. But the fact, you have to be very careful. Look where, in this case, the flow batteries are. It's down below the line, which is indeed not the same as what we saw on the previous slide. So you have to be careful. Don't take every publication at first sight. Okay? Just for completeness, these are then some cost figures from Schmidt. They have collected them in terms of the experience curves, as you all know, as a function of the installed capacity. This is, and here you have then the distinction between then what it is for a stationary system, for a system, for portable, for instance, for batteries, and also then a pack, also for transport. Oops. I'm losing, oh, okay. All right. What did I do? I hit this thing. Now let me just say a few words about the current status of these things. Well, this is a picture I took 2014. It clearly shows in power discharge capacity that the pump hydro storage 140 gigawatts. Whoop. Compared to all the others, that little sliver that you have there. Now, things have changed a little bit in the meantime, but not all that much. So I took an update from 6 months ago. That's in the IEA report from December. Okay, I have concentrated solar power. We don't have time, that's molten salt. I'm not going to dwell on that too much. You have there in the middle pumped hydro and batteries on the right-hand side. So that gives you the difference in gigawatts, this power capacity. So it's about 150 gigawatts for a little more for pumped hydro, as we just said a minute ago. And for batteries, well, if you give and take, I would say 10 at this moment, right? This is the projection then that they also make for 5 years or 6 years from now, which is then in 2026. So you actually could see that the expected increase in pump hydro storage will be of the same order of magnitude as for batteries. Now, but just be careful, because now we're looking at the energy capability. Okay, we just looked at the power discharge capacity just a minute ago. Look at 2020, pump hydro storage. Oops, it's all blue. And a little bit of the others. In 2026, that would be a little bit different. Now, if you want to have the details, look at this. You can look at it afterwards. I'm not going to run through this. Now, you might say, oh, that, yeah, okay, yeah, but be careful. Look at the scales. The scales are quite different. Okay? So, what I'm actually trying to say is we all tend to talk about batteries, and batteries are going to be the future, I think, together also with hydrogen. So the choice of the organizer is actually quite well. But don't forget pump hydro storage, because this is what is expected to be because of existing infrastructure in some of the countries where they have already big lakes that you would like to put then turbines, etc. So it is indeed then quite substantial worldwide what this might be. Okay, these were the technologies. Let me then say a few words about the applications. Well, you can use this thing for lots of things, as you can see, as a function of the discharge duration and then also again the power discharge capability. If you look at a table, here you have them seasonal storage, arbitrage, and blah, blah, blah. Now, it's a bit sad that in the literature you read a lot of these things, but they're not all very consistent. Now, I kind of like what Schmidt and his colleagues have done. They started from 25 so-called unique purpose applications, and then they grouped them in 12 applications. And I'm just going to concentrate on 4, because they're actually quite well explained here. So energy arbitrage is a difficult word for just saying, well, you buy electricity to store, so you buy electrical power to store in energy, okay, when the prices are low, and you sell it when the prices are high. Okay, then you have then peaker replacement. This is just if indeed then if at some moment you need just to replace gas turbines when you want to have the peak load. Okay, then you have seasonal storage. That's long duration storage. I don't think I need to explain much more. And then you, for instance, also network operation. That's then TND, the deferred investment. So this is the arbitrage. Okay, so the profile that you see there on the left-hand side, the profile that you see, what is a dirty green, is the price profile. You have determined a priori, okay, when the price goes below this thing, we're going to charge. If the price goes above that, we're going to discharge. For electrical engineers, I think this is an easy way to look at. These are the different types of reserves that we always need for let's say this is for contingency. Also there then the battery, in this case it might be batteries, very likely batteries will then help in doing what is to be needed. I also have to say a few words about power to gas, but since there's a speaker after me on the power to gas, I'm not going to say too much about it, but this is kind of a picture. It was a simulation coming from German reference. What you see here is it's the residual load that is shown. So it's the load expected in 2050 or projected in 2050, because nobody can predict the future, 80% renewables, and you subtract everything that was done by solar and wind, and then what is then the residual load or the net load, and these are then the gray things there. Sometimes when they're negative, that means that you have a surplus, you have way too much renewable electricity. Okay, if you are positive in the white part, that means you have a shortage. Well, look at the thing on the right-hand side. This is what they call a Dunkelflaute, maybe 2 weeks, no wind or hardly any wind or hardly any sun. We need then something to cover that, and very likely that might then be a gas, might then be an interesting gas, hydrogen, etc., but I'll leave it to the colleague after me to talk about that. It's a bit this type of scheme. I've made this scheme here for for methane. It basically says you have superfluous electricity, you put it through an electrolyzer, then you mix it with CO2, and then you have natural gas, and you put it in the natural gas system. But Dr. Schmidt is going to talk about that in a few minutes. This is somewhat the same, so it's a luxury for me that I can just click, because he's going to talk about those things, and if he doesn't, then you can always go back to my slides. Okay. All right, let me then just stick a few a few minutes more on the storage applications. Okay, this is an example for the United States. It says for the long-term seasonal storage. So I'm not going to talk about the details of power to gas and power to hydrogen. I'm just going to show why it may be needed. This is for the United States, a 100% decarbonized system that they modeled. 94% would be variable renewables, plus hydro and geothermal, and 6% would be thermal generation, but then coming from hydrogen and or biofuels. This gives you an idea of, at the bottom, this gives you the green one here, the curtailment of PV and wind. So these are times when they have way too much wind or solar. The other places, of course, that's when they don't have enough wind and PV. And you see then on the top that, of course, you need then thermal generation to make up for that. Okay, and that's indeed then where it will be needed. And these are then moments that can be quite large. If you see that from July the 1st to, let's say, to September, that is indeed then where you might run into troubles, at least in that region where they simulated it. In Germany, the word, they have generalized not only Energiewende, but also the word Dunkelflaute comes from there, the cold spells, the dark doldrums, as they also are called. And this is then a publication from Runau and Cubis, it's very recent, that they looked at 35 years of weather history, okay, with lots of wind and off and onshore PV in Germany. It's a 100% optimized, decarbonized system. And this is a typical thing that people then see. So the positive thing, that is the generation, the negative, that is demand. And if you then see the green that is hatched on the bottom, that is then electricity that is being used in electrolyzers. Okay, the gray thing on the bottom, that's thrown away, that's curtailment. If you see then on the top, the green with that is hatched, that is then using hydrogen to produce electricity. That's the typical type of Dunkelflaute that people consider. Now these guys, they said, yeah, wait a minute, but that's not enough. Because this would still be pretty easy, quote unquote. In these 35 years, we have actually found that there is a period of 61 days that is a pretty scary period. Yeah, that the lights would go out if you don't have these things. So I invite you to just look at this, this publication. They say, well, if you have from time to time a little bit of wind and solar generation, it isn't enough to cover the whole thing. So it's a cumulative. Now you could say, once in 35 years, well, turn off the lights, I don't care. Well, try to explain that to the population. So this means indeed that the long-term energy storage challenge will remain there if we want to continue that way. This is just for your information, and I'm not going to follow that. Then for peaker replacement, that was that, you remember that duck curve that I started out with? Well, it actually turns out, and that's what the folks from Endwell found, the more renewables that is for California that you put into the system, the shorter the time is that you need to cover that residual load. And that's, of course, then a place where batteries might come in very handy. Okay? This is also for your information. If you want to have a bit more detail, be my guest to look at that. I just have 5 minutes left, or a bit more, than for the levelized cost of storage. This is work that we have been doing as well. But we started this, and we also, I don't know, it's now 5 or 7 or 10 years ago that with the European academies that we also tried to make some sense of this, that there's so much confusion about what was published in these things. Let me then, for that, just recall what we mean by the levelized cost of electricity. That's relatively easy. It's actually the average fictitious electricity price that allows break-even considering all the discounted costs by means of net present value. Okay, this is the formula. It looks a bit complicated, but it isn't. Just look at it. Take the numerator. Okay, you have there the costs. That's the costs at the numerator on the right-hand side. So you have the overnight capital cost. You have the operating and maintenance. Okay, you have the fuel cost. You have maybe a CO2 cost, and you have a dismantling cost maybe. Then you have to bring that back to today by discounting. That's the factor that you have 1 plus r to the minus t. Now, if you look at the bottom, okay, that megawatt hours, put that just for a second on the left-hand side. Okay, and then the left-hand side would then be the revenues that you need to cover the right-hand side. Okay, and that is then, what are the revenues? It's the amount of megawatt hours that you have produced, okay, times the price that you want to see, and indeed that price is then the LCOE. Okay, so that's effectively what it says. I like to look at it as the price is the price that you are required to see to cover all your costs, but it is clearly a cost measure, right? Now, so if you just look at all these things, so you have the costs on the right-hand side has to be balanced by the revenues by selling electricity, by producing electricity. Now, I just have added this thing just for your interest. if you want to see this thing in a transparent way, the thing that I wrote here in red, I would say once you've seen it, if you've seen it once, you've seen it always. This is all for discounting. So kind of visually ignore it and concentrate on the other stuff that I put here in green. Okay, that makes it much more transparent if I run through some of these sometimes awkward formulae. So what is now the levelized cost of storage? Well, now it's the average fictitious electricity price that you want to see during discharging to allow break-even of all your costs, including the charging cost, the fuel cost. In this case, that's the charging of the electricity. And very often in the literature, that's ignored. Okay? Now, these are things that we have done, new metrics that we came up with. I'm not going to read this thing, you can read it later on, but it's then what we call the required average discharge price. It's the price you want to see, including all the costs for capital, for O&M, for charging electricity, etc. Okay, that's for me the proper LCOS. Again, I have the same formula, but now I have added a D there. The D stands for discharge. So it's always per unit megawatt hour discharge that one does this. And indeed, this is now the little formula. It's the same thing. I haven't told anything new. I'm even going to simplify that and say, although for power to gas maybe there might be a CO2 cost, but okay, let's ignore it to keep it simple. And so this is now what we have. But take into account what I had there before. Let me just go one step further. So the light orange there, that's the average cost per charging cost, but per megawatt hour discharge. Yeah, but actually what you do is you do that per megawatt hour charging. And of course there are efficiency losses. So you have to be very careful on how you do these things and how you play with it. Okay? Okay, so that's what I just said. Just to show you what are the types of metrics that we came up with that we think are very relevant, and we also have some details and compare them with the market prices in the publication. So this is what we say the required average discharge price. That's the one that I've just talked about. So this is the one we concentrate on, and the TCC, that's the charging cost. It's included, okay? The fuel cost, you would say. Then you have the required average price spread. Okay, well, that's actually the difference between what you sell and what you buy, but if you then just play with it, then this is what comes out. And there you see that the only thing that is left there, your charging losses. So this includes your charging losses. Okay? Or basically, it's the 1 minus RT there. Huh? They're the efficiency losses. And then you have the operational profit. Well, the operational profit, there you see this is an equation for charging cost equal to 0. This is what other people sometimes call the LCOE. So it is different, and I warn you, be careful when you read these things in the literature, because they might all differ. And regrettably, most people use or publish these things to their own benefit. So just to show you, these are the things that we then came up with. And I would have loved to talk another hour about this, but time is not helping us with it. Now, this was mostly considering, what I did before, was mostly considering, so what I did here, mostly considering energy arbitrage, buying, selling, etc. But we said that it is also very important for ancillary services, and that's where indeed then the power cost is also something that is very important. So there is also a metric that I've stolen here from Schmidt et al., which is it's the LCOS-P. So for power applications, it's actually the power-related annuitized capacity cost. So there is a different metric that you have to take into account for that. Now recall these things that we've seen before. I'm now going to concentrate on 3 of them. The yellow is energy arbitrage. The purple is going to be secondary response, which is effectively, it's basically frequency, let's say balancing that you try to help, okay? And then seasonal storage, okay? Now what Schmidt have done is the following. They've said, okay, let's just fix the charging cost at $50 per megawatt hour. Fine, that's an assumption. And then they've said, look, we have for each of these applications on this previous thing here, for each of these applications, we are going to just impose and say we need so many cycles and we need so many discharge hours. Okay, that's a bit arbitrary, I know, but at least that's what they've done. That's an interesting exercise. And you see a whole bunch of these things. Now you remember what I just told you here: yellow, purple, and then pink. Okay, I've tried to play a little bit with that last weekend. My wife wasn't very happy, but anyway. So these are the three that we looked at, and this is purple. You have on the left-hand side seasonal storage pink. In the middle you have energy arbitrage, and then secondary response here is in purple. And this is what they did. They did a lot of simulations, etc., and these things, and that's 2020 and 2040. This is now the levelized cost of storage, with a charging cost of $50 per megawatt hour. If you first look at the left-hand side, and also at the legend, then you see what is green, that is quite well done. When it's red and dark thing, that's prohibitively expensive. So what you see on the left-hand side is that indeed an arbitrage is quite well doable these days. Similarly also for secondary, that's the one, the purple here, for secondary reserves. And then on the left-hand side on the top, that is seasonal storage. Well, it is in the orange line. Now, if you move to 2040, then you see that actually the lines have shifted and that things are expected to become more affordable. On the next slide here, what they did again for 2040 and 2020 and 2040, in this case, they looked at which technologies would be doing that. On the left-hand side, you see that yellow first, that arbitrage these days is mostly done by pump hydro storage. Then the purple, also at this moment, pump hydro storage. That's secondary frequency regulation. Okay, and on the pink, it's on the left-hand side, that is well in between compressed air storage and hydrogen. So hydrogen is actually looking there over the shoulder, let's say. On the right-hand side, you see that for the pink bullet there, hydrogen would be the winner. And you also see then, that's then down below here, okay, that you see both for, on the right-hand side, I'm looking now at the red block, that both for arbitrage and for secondary frequency regulation, that the batteries will come in, or are expected to come in. Okay, one final thing, and then I will conclude. Just look a little bit at, now we're going to look at a different reference again, but for these two things, what is then energy arbitrage on the one hand and peaker replacement. This is from the reference here on the right-hand side, and look first there above what I said here, because as I told you, also the terminology is not equal everywhere. So what we called arbitrage in the previous slide is also called time shifting by these folks, and peaker replacement is the same as firm capacity. Okay, it's just that as a vocabulary translation. And this is what they expect for the future. This is not for the United States, but expect for the future when you do these services that we just looked at the previous thing. If you do service stacking, if you say, well, I have invested in this battery, for instance, it can do several things. It cannot just only do one thing, it can do more things with that. And there you see that the fraction for time shifting, which is for arbitrage, that's the orange thing, is, yeah, okay, not bad, but clearly the winner there is that one for firm capacity, that's actually for peaker replacement. That's where indeed most of the money, most of the value is. And you see if you add them together, that's then the light blue curve. I would have loved to continue speaking for a much longer time, but time is pressing us. Okay, so my conclusions will be very brief, and I would say relatively clear. Storage clearly will be part of the flexibility options in the future. Maybe I should have written will be a very important part of the flexibility options for the future. But the value of storage will depend on the system characteristics. It will be different from place to place, so it depends also on the market design, the price differences, the other flexibility means that are available. For instance, if you talk to the Dutch people, then you might, well, they might actually fall asleep in part of this thing when I talk about pumped hydro systems, because they couldn't care less, right? But I know in this country, pumped hydro is quite important. And then at the bottom there, much more research is needed to fully understand the relative role of storage compared to the other flexibility options, especially now that we have introduced sector coupling as one of the major flexibility issues for all applications in various systems. Thank you very much.
Yes. Thank you very much for a very interesting and comprehensive overview of storage and different applications. And I open the floor for questions. So, any questions? Yes, and please state your name. No, it's you, please.
Yes, my name is Ole Inganes. There were many numbers. I've forgotten most of them actually. But you stated that curtailment and energy loss during storage are two aspects of a similar phase. Considering now that the generation of that curtailed energy is becoming cheaper and cheaper by the year because of learning curves, and the same thing happens for storage, when should we expect that it becomes a more appropriate thing to do is to overinvest in renewables and store that for that time? Will there be such a time?
That I can't say. I can't look into the future, but I would say I would broaden it up a little bit because storage will always be in competition with the other flexibility options, especially demand response. And for instance, if you look at what might happen in the homes, and the question that is, should they opt for batteries when they put, for instance, PV on the roof, batteries, or should you opt for demand shifting? So the first thing that folks would say in electrical engineering that, first of all, try to use all the electrons that you have produced. And if you can do that, for instance, by shifting, and they do that in an easy way, that's of course then that's the winner. Okay. As soon as you start introducing storage, okay, you might also shift, but at a cost, because that is the cost has to do with your losses, which is then de facto curtailing some part. But you're right, and that you will see in all future projections, you will always have curtailment. The reason is that, first of all, that indeed in the future it's expected that PV costs and wind, solar, that they continue to go down. So maybe it does make sense to overinvest a little bit, if I may say so. That's the first thing. And then, of course, then you might come up with so-called superfluous electrical energy. The question is, what are you going to do with that? And that's a big discussion now at this moment. You have then the hydrogen folks say, let's make as much hydrogen as we can, and maybe Dr. Schmidt might tackle that. You have other people say, oh, wait a minute, before you start doing that, use all electrons where you can. So try to electrify industry as much as possible, and heating, etc., and these things. But you will always, and then you will have to find a balance of storage, short-term, long-term, try to avoid as much curtailment as is possible by sector coupling and by storage. But as I said, storage will always have to compete with the other flexibility means, and it's an economic optimization at some point. One thing you should never forget is that we will indeed have to accept curtailment of renewable electrical power. Now, you might regret that, and for an engineer it's very difficult to see that. But the fact is, if indeed then the investment costs for wind and solar are becoming so low, it might indeed then help. And also, you don't want to over-dimension your, for instance, transmission system. Because if you have to dimension your transmission system to capture or to transmit the very last amount of electrical power from one region to another, you're over-dimensioning for something that might be used only half an hour per year or something like that. So you have to accept that. But in the end, it will be techno-economic optimization, and all these technologies will have to compete against each other. And that's why we have to be very, very careful with slogans, and we have to trust that people do correct, good system analyses, that we also scrutinize them. Did they use the right assumptions, the hypotheses, the boundaries, etc., and all these things? And let me say one more thing. If you read the document and they don't tell you what the assumptions, the hypotheses, or the system are, throw it away. the results are worthless. Because you can produce, you can sell anything you want. And certainly in this domain, you have to tell people what are your hypotheses that you use. There's a long response to a particular question.
Thank you.
Please.
Thank you. That was a question. Yes, please.
Yes, my name is Carl Hogue from DeepGrid. I have a question about your very colorful chart at the end where batteries didn't pop up as useful for any of the use cases that you displayed. But there is a lot of investment going into batteries, which you showed in the previous chart. So why do people invest so much money in batteries if they're not suitable? Those are the charts I'm referring to.
Yeah, this one? Yeah.
Oh, yeah, and then next ones as well.
These ones, okay? These ones.
Oh, that's the one I was referring to. So you see batteries are not really there in 2020 anyway. Right?
Well, the thing is...
Lithium-ion, for example.
Well, the thing is, if you look at... now, this is more on a wholesale level that this is looked at. What is the most, let's say, the most applicable technology that is being used to do that type of functioning. And here it's clear that most of it is done, on the left-hand side, for instance, most of it is done by pumped hydro at this moment. Okay, batteries do a little bit, but that's negligible compared to everything that happens there. But the good news, and that's what you should be looking at, that's what you see, and that's because people are investing now and learning that the cost of the batteries is going down. And you see that ultimately, that very likely, and that's just now 2040. I could have given you also 2030. I think they already come into the market in 2025, 2030. But I think they give every 5 years one of these spots, so please check the literature. But of course, let's be honest, for batteries in the homes, I think in most countries, if I'm not mistaken, they are supported by government, by tax credits or by subsidies or these things, which means that they're not there yet to enter the market. Then the whole thing of electric vehicles and batteries for electric vehicles, that's completely different environment. Okay?
Thank you. Any more questions? Yes, please.
My name is Dan Larhammer. I'm not in this field at all. I'm just the president of the Academy. I'm wondering about the cost of lithium batteries. There have been concerns that the supply of lithium will not be sufficient for the demand in the future. The diagram you showed was a price decrease by 80–90%. Will the prices go up eventually?
Well, I think that's the question. It has to do with, well, I think if you look at the amount of lithium that is available worldwide, I think there's plenty of lithium available. Right? For instance, the nuclear fusion folks have also been looking at that because they need lithium to produce their tritium, etc. and these things. The question is, do you have sufficient mining? And what you have seen over the last decade or 20 years is that the Western world, if I may say so, Europe, the United States, they basically disregarded this thing and they've left everything to China and to Russia to do the mining. Because it's dirty work and we didn't like to have any mines anymore and these things. So I think it's all a question of investing in clean mines, okay, or try to, well, I think the Western world won't have a choice. Also for, it's not only lithium, but also the rare earth metals, etc., and these things. So it's the same thing. So the price will always depend on what is available at this moment, well, what is available at the supply. So I'm not too concerned. It's very likely that the prices will go up for a certain time, because if the prices don't go up, nobody will be interested in investing in new mines. If the prices stay up for a while, then there will be investment in new mines, after which then the prices will come down again. So you always have to be careful also with the price of these basic materials. It's a cycle, I think, and it has to do with the investment cycle in the production capacities of these things. So we all know that we live in a turbulent world at this moment. I think the world geopolitically, etc., and also will look differently 10 years from now than it is today, because then Europe, North America will start to do much more themselves. They call it what is now strategic autonomy or something like that, and is then by means of trying to get more things here, that they want to assure that there is sufficient of those things, but very likely it will be more expensive still, because, for instance, the labor cost here is higher than, for instance, it is in China and India and these things. So we also, and now I'm going very much beyond my field of expertise, but as a citizen, I could say, maybe we have been a little bit too complacent and we have outsourced almost everything to third parties, where they did these things cheaply and abundantly. And maybe we'll have to reprogram ourselves and do part of it more ourselves, but it will be at a cost. But if your question is, what is will there be enough lithium available? I would be tempted to say yes, but at a higher cost. And there again, it will then come this nice curve that we have seen for battery decrease. Will it continue a little bit? I could have shown some other figures what the IEA thinks. They actually expect that for the next 5 years, that probably also for PV, for wind, or for manufacturing costs, and for batteries, that the price will probably go up a little bit, but then hopefully will come down again afterwards. So there are very interesting things going on these days. And so if you want to invest in something, be a bit careful these days. Maybe wait a few more months.
Okay, time flies, but I have a question, and that is concerning market design. You mentioned that on several slides, that market design is important in other regulatory issues. Could you say a few words about that? Are the market designs optimal to utilize all the flexibility we have today, or how should it be changed to obtain that optimality?
Well, now you're asking, how should I say, a $1 million question or something like that.
Yeah, well, you're good. So.
Well, let me first say a disclaimer, and that is that at this moment, in the framework, let's say, of Europe, there's actually a massive discussion going on what is the best market design for the electric power sector. And you have then indeed and the believers in the free market design as we have it today. You have then others who say, no, the state should be much more involved and it should be much more strict, and we should maybe go back to a certain extent and to the previous thing. So I have no idea what type of market system we will come up with in the future. Now, what I think should be done, and I'm a firm believer, I think the free market principles, I think I like them, in the sense that you allow technologies to compete on a fair basis with each other. As long as there are no market distortions, that maybe some technologies are more subsidized than others, etc., or long-term contracts and whatever, if they can compete on a fair basis, then I like that. But you need very good regulators to actually then say what the system boundaries are and what can be done and what cannot be done. And that's, of course, then a discussion which I don't think it has been solved yet. One of these, I don't know exactly what I think I know a little bit, but I don't know exactly what the market system here in Sweden is. But you have, for instance, in the United States, a big discussion between what they call then the energy-only market. And for instance, that's where they say, okay, with the price of energy, we can do everything. And if there is a shortage of energy, then the prices, they are allowed to go in the 10,000, even $50,000 per megawatt hour for a little short of time. And this will be well enough to give an incentive to have new investments, etc., etc. There's some strong believers there. ERCOT in Texas was a typical example, and it worked reasonably well. And of course, they had the problems there in February 21. The political world is trying to get involved. I'm not sure what's going to come out of it. Then you have other markets that say, well, energy is one thing, but we also need the capacity to be there. If you have then a capacity market, which means that you can also bid in and to provide the delivery capacity at the right time, that's also might be an opportunity for storage. So I think what storage is going to do is a bit subject to which choice people are going to make for those two things. You have then a third category, like half of the United States is still a regulated system. The utilities are still vertically integrated, everything they're done by themselves. But I think still, even in that system, then the utilities themselves would like to optimize their own system. Okay, maybe less sector coupling and these things. So I don't know, and I realize I haven't answered your question, but I've talked around it. But it's a tricky question. But I think we should have. It should always be very transparent, as little as possible market distortions, and let indeed all technologies compete with each other. Define your system, define also what your hypotheses are, and make sure that you have independent and competent regulators. I would leave it at that.
Okay, thank you very much. Time is flying, and I think we have to stop there. Thank you once more for a very interesting presentation. And now there will be a coffee break out here, and please be back 20 minutes past 10 here. Then we will continue.
Okay, thank you very much for coming back after the coffee break. And we will now continue with our second presentation with the title Energy Storage Using Power to X. And it will be given by Professor Thomas Schmidt, who is a professor at ETH Zurich and also the chair for the electrochemistry there. And he is also the head of the research division Energy and Environment at the Paul Scherrer Institute, PSI. And he has been the director of the Swiss Competence Center for Energy Research, Heat and Electricity Storage. Professor Schmidt has a university degree in chemistry from the University of Ulm in Germany, where he also obtained his PhD in chemistry. Professor Schmidt is a fellow of the Electrochemical Society. In 2022, he was also elected fellow of the Swiss Academy of Engineering Sciences, SATV. So, bitte Thomas.
So thank you, Göran, for the nice introduction. So I'm going to talk about power to X. And I will explain later on what power to X really means. But certainly I don't want to talk only about the technology itself. I would bring it into a context, right? And I think that is always very important, and also as William described before, you need to look from a systems perspective into different technologies in order to see actually what makes sense at what place and why sometimes it may not make sense and another technology will make more sense, right? So that's why the systems perspective is also very important. So I quickly want to go into, because that is sort of setting the scene a little bit for what I will be talking about what we are doing at PSI in the research division, energy and environment. And certainly you can see the vision and mission, which always sounds very, very nice. And but what is very important is the background, why we are working on these different topics, and that is actually the Swiss Energy Strategy 2050 with individual goals. There's a net zero strategy. Net zero means net zero emissions, and there are the climate goals, and that is our context where we are working in. And just from a top view, what are these goals from the Swiss government? It's or the Swiss Energy Strategy. Switzerland will phase out nuclear energy, and that needs to be replaced by so-called new renewable energy technologies. And new renewable means all the renewable technologies which is not hydropower, because that is already existing in Switzerland very broadly. About 60% of the Swiss electricity is produced by hydropower. So that is one of the goals, replacing the nuclear power plants. Then the other goal is improving energy efficiency. So you will have a seminar in September on this at this place. So we need to improve energy efficiency for specific technologies and applications. And there's also in the strategy the cap of the electricity consumption per year to about 60 terawatt hours. So that's sort of the cap. We don't want to use more. Right now we are using about 60 terawatt hours in Switzerland. And then there comes the climate goals to reduce the CO2 emissions to minus 50% by 2030 in comparison to what there was in 1990. And then the last one is actually Switzerland wants to be a net zero country by 2050. So these are sort of the boundary conditions we are working on, right? And that is also the context what I'm going to talk about. So let's quickly talk about the Swiss energy transition. So if we look at this, what we have been doing in collaboration with other institutions, with one of the Swiss, within collaborations of the different Swiss competence centers of energy research, actually PSI and our laboratory for energy system analysis was actually calculating different scenarios, what would be the cost of the Swiss energy strategy, right? And so out of these different scenarios, actually there is one take-home message. One needs to have investments on top of what one would pay anyway, right, in the current situation, of about 150 to 300 billion in that range, Swiss francs for 30 years, like between 2020 and 2050. So that makes about 5 to 10 billion Swiss franc per year, which is about plus minus 1% of the GDP. And these numbers actually, if you compare them with a study from the Boston Consulting Group and the Swiss Bank Association, they found about 350 billion Swiss francs. So that is roughly the same ballpark. So that is the anticipated cost in new investments if we want to really go this transition to reach the climate goals and to reach the net zero goals, right? So now to bring these numbers in a context, Switzerland has about 8.6 million inhabitants, right? So if we just take the number 300 billions over 30 years, that makes 10 billion Swiss francs per year. And that is about 1,160 Swiss francs per capita in a year as cost, right? And this is about 3.2 Swiss francs per capita in day until 2050. And to bring this number into context, if you buy a cappuccino in Zurich, you pay about 5 Swiss francs, which is about 50 Swedish krona. In Stockholm, I just checked yesterday, it's about 4 Swiss francs, about 40 Swedish krona. So that is actually what we need to invest. 1 coffee, 1 cappuccino a day. So 300 billion over 30 years can be broken down to this and becomes a little bit more tangible, and all of a sudden it doesn't seem to be so much anymore, right? So it appears to be feasible, right? Because I don't think about if I want to have a second or third cappuccino if I'm in Zurich, I just buy it, right? I don't think about, well, this is an investment I don't want to do. So it becomes sort of feasible and in a way also a tangible number for everybody, right? So this is the cost we are actually talking about. Now certainly, let's look a little bit into okay. So let's look a little bit into negative emission technologies, right? So these are the goal of negative emission technologies is actually that we permanently remove CO2 from the atmosphere, which is important actually to achieve net zero targets. And certainly we need to do something in order to compensate for these emissions in these sectors where it's very hard to avoid to have CO2 emissions. That in some industrial sectors and in agriculture, for example, also what is very difficult to replace or to decarbonize is aviation sector, transatlantic flights. That's a very hard to decarbonize sector actually. Now, certainly, the open questions are always like costs, the potentials, what side effects we may create, how permanent we actually can remove CO2 out of the atmosphere, and certainly what we mean about sort of net negativity, and certainly we need to have a legal framework for everything, which is not necessarily be given. So, if we decarbonize Switzerland, we actually did some energy system modeling, and then we basically are looking or can look at the trajectories, right? So basically, if you plot like a baseline scenario, so this is sort of the trajectory if we would do sort of a business as usual, we are maximum capable in Switzerland to reduce the CO2 emissions by 42%. If we just calculate a scenario where we follow the targets of the Swiss energy strategy, which actually became a law after a public vote in Switzerland, we can only reach a reduction of 70%. And basically what we need to do is sort of a net zero scenario where we reach 100% reduction, so that we are net zero at the end, right? So the question is, how can we do that? So what do we need to do? What layers are important in order to be able to go there over this time span, right? And in our model, you may see at the bottom, I mean, there are different modules, a resource module, there are import-exports included, there's a transformation module, a storage module, then transport and infrastructure, and then the energy demand side. Yeah, so that is included in the model. So it's a pretty holistic approach in order to get an understanding on the different scenarios we need to talk about. So the question is, how can we achieve net zero in 2050? And so you have these different sectors: industry, services, transport, residential, and transformation sector. So if we look at the transport sector, we need to decarbonize minus 16 megatons of CO2, right? And that only works in a scenario where about 80% of the cars are electric. And in the heavy-duty transport, we have about a third of hydrogen-fueled heavy-duty vehicles. And half of the heavy-duty vehicles need to run on synthetic or biogenous fuels, right? And the final energy consumption of the transport sector in this scenario is more than minus 50% to what we have right now. Now, if we, well, sorry, I go back one more time. If we look at the transformation sector, we need to decarbonize by minus 5 megatons of CO2. So we need to install about 30 terawatt hours of new renewable sources. We need to have a power capacity of about 2 gigawatt for batteries, and about 11 terawatt hours of hydrogen being produced. And there you see already with the transport sector, with the transformation sector, hydrogen comes into play, and hydrogen is produced by power to hydrogen. So hydrogen would be one of the axes, of the possible axes in power to X, and I explained a little bit more in detail later after I came up with this overall picture. Then let's go to the industry sector. We need to reduce minus 5 megatons. We need to have improved integration and savings, CHP, so combined heat and power and district heat, including hydrogen, so also their hydrogen might be used for district heating. In the service sector, also minus 5 megatons of CO2. So that is sort of an efficiency sector where we need to improve building insulations, for example. Then certainly using much more heat pumps. They are supposed to deliver more than 60% of the heat demand in the service sector. In the residential sector, again, it's minus 9 megatons, also building and insulation. And there we need to really ramp up heat pumps in order to provide the heat needed in the residential sector. So this is sort of the scenario we are looking into. Oh, sorry, don't want to skip this one. So what you actually see there, and that is very important in the gray bottoms or gray balls, specifically from the industry sector and the transformation sector, what we need actually in order for the scenario to work, we need to have some CO2 capture. Right? That means CO2 capture and then storing it somewhere. Yeah. So without a CO2 capture, without CCS, we will not be able to reach this scenario. So, and this is certainly also in line with the title of the seminar series about transition to an electricity-based energy system, also in line what William was talking about before. Electricity gains a lot of importance in the energy system if we want to decarbonize. Yeah. So in our scenarios, not only certainly the production mix is changing considerably as compared to what we have right now. It is also that the final demand of energy, right, is actually in this final demand, the electricity consumption is certainly, or the part of the electricity is actually increasing significantly. So what we also need to do, we have a lot of waste incineration plants in Switzerland where we need to install carbon capture and storage or carbon capture and utilization to use the CO2 to produce something, use it as a carbon source. And certainly one of the side effects we're actually having by increasing the electricity demand, right? We need to have a flexibility when it comes to trading electricity, right? So we need more, but the country need to avoid to be too dependent on electricity imports from other countries. Right? Because the question is certainly, because at the end of the day, all our neighbored countries in Switzerland, I mean, they are doing similar things, right? In different colors maybe, but they are doing similar things in order to reach net zero societies, etc., etc. So the question is, are they able to export electricity to Switzerland? Yeah. And the question is, are we able, in return, at some other time, maybe export electricity to Germany or to Italy, right? So this trading becomes significant, or will become significantly more difficult as it might be right now. So certainly, due to a lot of decentralization, we may have a shift of production of electricity to lower grid levels, right? It might not be the large power plants anymore. They are feeding into the transmission grid. It might be more local and directly fed into a distribution grid. So there will be a shift. And system flexibility will be, and this is also what William was talking about before, system flexibility will be through hydropower, battery storages, and demand-side management. And on the demand-side management, there's one aspect. It's what is called here smart e-mobility with V2G. V2G means vehicle to grid. So that means in specific, under specific conditions, a battery electric vehicle, which is actually being charged, might also be discharged for the grid, right? The question is how to implement that, and that is a completely other discussions, right? Because does the individual would allow that? Do I want to have my battery car being used to stabilize the grid? That's an open question if people want to do that. But that's actually an option because with 80% battery electric vehicles, a lot of storage capacity is actually around, and most of them are not at the same time on the road. All right, so why not using it? So that's sort of the basic idea. And then certainly last but not least, again, it's the seasonal storage, also what William was talking about, and the seasonal storage in our scenario here is actually by using hydrogen. This is a little bit, just a quick overview on the seasonal electricity supply in 2050 in the net zero scenario. I mean, we will need to have, in winter, we will need to have imports still, right? And this is about 6 terawatt hours in 2050. But certainly in summer, we will have surplus, which actually is used then for producing hydrogen via water electrolysis, and some to be shifted to winter and some to be shifted into the mobility sector. Right? So that's also sector coupling, right? So what is important here, I mentioned before, CO2 capture. It will be a must to achieve net zero in a cost-efficient way in this net zero scenario. And that actually, so we need actually sort of negative emission technologies to compensate remaining emissions which we cannot carbonize. So that's why it's called net zero. So there will be sectors where CO2 is emitted, but others which are actually consuming CO2. So net zero overall means overall there's a zero. Yeah, and if we look into this diagram, so actually we need to capture CO2 from hydrogen production. If it's via steam reforming, for example, of natural gas, we need to capture some in industry sectors and from electricity production. There will be also in this scenario there will be CO2 trading. Within Europe at least. Relatively large amount will be also traded, and about 2 megatons of CO2 need to be sequestrated domestically. Yeah? And only a very small amount actually in this scenario is actually used for synthesis of fuels. Now let's talk about power to X. I was talking a lot about hydrogen. So where's the hydrogen coming from? Let's talk about power to X. So that's a very general plot or sketch on the principle of power to X. So on the one hand side, you have the sources of CO2, and you have the power sources. So these are sort of the two input parameters to a power to X system. So first of all, let's start with the power side. That's on the left-hand side, the yellow, sort of the sketch of the grid here. So you have electricity. You need to use the electricity to produce hydrogen by water electrolysis, right? As a byproduct, you produce also oxygen when you split water, and oxygen actually is a relatively valuable chemical. So it's not like that you would necessarily need to vent it into the atmosphere. But you can also use it. So it's a product in chemical industries, for example. And I will show also another example where it can also be used actually very, very effectively. Now the hydrogen, what can you do with the hydrogen if you're not using the hydrogen directly in a fuel cell, for example? So you can add CO2 from one of the sources, from power generation, from biomass conversion, from cement plants, for example, or from direct air capture. So you can use the hydrogen together with the CO2. You can do a methanation reaction, so you have synthetic natural gas. So that's one option. The second option, together with carbon monoxide, you can actually do Fischer-Tropsch synthesis. And produce large-scale or longer chain hydrocarbons like kerosene or diesel and so forth, right? And these are Fischer-Tropsch plants are huge plants in many countries of the world in order to produce diesel, right? Which we are using in our cars right now. You can also produce methanol out of it. Methanol is a sort of a precursor in chemical industries, for example. So out of methanol, you can also produce propylene, ethylene, and all these things used in chemical industries, which is highly important. You can also use the hydrogen together with nitrogen to produce ammonia. There's a huge ammonia demand in chemical industries for fertilizers, etc. Right? That's large-scale application. So hydrogen actually is very versatile. Yeah. So it's an energy vector, if you will, but also sort of a product vector, because it not necessarily is going to the energy sector itself, because a lot is actually could be used in chemical industries. Just to give you a rule of thumb, the energy equivalent in hydrogen used in German chemical industries is about 60 terawatt hours annually. Yeah. So that is actually what whole Switzerland currently is using as electricity. So that's the hydrogen demand in Germany just for German chemical industries. So it's a huge sink. And this hydrogen actually is coming from steam methane reforming with CO2 emissions. So one way to decarbonize the chemical sector is actually by producing hydrogen via renewables. But it's really huge amounts. We need to be able to do that. so the scaling is enormous if you think about that. Okay, so that's sort of the general power to X. So you see the X can be really manifold. The X could be also heat, right? It could be power to heat if you want to do that. So let's stay a little bit with hydrogen. Power to X and is actually used, and the hydrogen used is for seasonal storage, because that is providing the flexibility and enables sector and energy market coupling. Yeah. So we need to, in our scenario here, about 6 terawatt hours is produced by electrolysis, about 3 by steam methane reforming or orthothermal reforming, together with carbon capture and storage, and some from wood gasification. Yeah. So about 1.6 to 2 terawatt hours is shifted seasonally, and the rest is actually going into some heating applications, industrial sector, residential or commercial applications, transport, freight transport and passenger transport sector. Yeah. And also some is actually used for fuel synthesis. Yeah. So if you look at that, hydrogen goes or allows actually to decarbonize the different sectors in to a certain amount. Yeah. Now, if we look at just at the greenhouse gas emissions of the hydrogen production, so it's relatively low for electrolysis, and basically what is plotted there is the gram CO2 equivalent, so that includes all the greenhouse gases per megajoule of hydrogen based on the lower heating value. On the right-hand side of the scale is the kilogram of CO2 equivalent per kilogram of hydrogen, so it's probably a little bit more handy scale, right? And certainly what one sees actually depending what technology one is actually using, then the greenhouse gas emissions are highly dependent on that. If you look for electrolysis, so for example these black triangles, so that's the EU 2017 electricity mix used to produce the hydrogen. You're ending up with sort of about 200 grams CO2 equivalent per megajoule. You have also different scenarios inside there. So GWP 100 or 20 means actually the greenhouse gas potential, how much you are actually want to decarbonize the technology. 20 means 20%, 100 means 100%. And so you really see that these dependencies along these lines. Now, let's go a little bit more on the cost side of hydrogen. And that is just a cost estimate. It's not as sophisticated as the method William was describing before, but interestingly, if you do a sophisticated analysis, you come plus minus 10% to the same value. So I just chose to use the easy way, right? So if you have a power price of 25 Swiss francs per megawatt hour in Switzerland, which is reasonable, so that is your input electricity. And you have an electrolyzer of 10 megawatt power, which costs about 500 Swiss francs per kilowatt. And it's operated 2,000 hours a year over 20 years. So that are just reasonable assumptions and also targets what actually industry wants to do in these sectors. And you can certainly play with the numbers, and then you're creating different values, of course. So if you have that, your cost of hydrogen is about 1.8 Swiss francs per kilogram, right? So if you then use a hydrogen-oxygen fuel cell, and this is actually where you can use the oxygen from the electrolysis, because a hydrogen-oxygen fuel cell is significantly more efficient than a hydrogen-air fuel cell, because you don't need to bring 80% of the nitrogen as a sort of inert gas through your system, right? So the systems are significantly more simple, and due to the partial pressure increase, you have higher efficiencies. So if you have a 3.5 megawatt hydrogen-oxygen fuel cell system which costs of about 200 Swiss francs per kilowatt, which is operated 4,000 hours a year over 20 years, you end up with about 80 Swiss francs per megawatt hour. If you consider electrolysis and a fuel cell as a storage application, right? That means electricity in and electricity out. Yeah, and you convert it in between at the time whenever you want. So if you look on the levelized cost of storage for lithium batteries and for different technologies, and this is in this Lazar's levelized cost of storage analysis, you find values for the different technologies between 85 and $640 per megawatt hour. So a dollar and a Swiss francs is roughly one to one ratio, plus minus. So we are actually in a ballpark where one would be able to compete in this scenario. Now, if you put or use the hydrogen for mobility, then the costs are about 1.80 Swiss francs per 100 kilometer, because sort of the rule of thumb for fuel cell electric vehicles is with a kilogram of hydrogen, you can drive about 100 kilometers. The new Toyota Mirai is about at 0.75, so it's getting better and better. But just as a rule of thumb, 1 kilogram, 100 kilometers. So that would be the cost of the hydrogen for driving. So also that looks relatively feasible and interesting, right? So right now, with the current diesel prices, which is about 2 Swiss francs per liter, with my diesel car, I have about 10 to 12 Swiss francs per 100 kilometers. So it appears to be feasible. Now, last example, power to X in aviation. And what I mentioned before, there are huge CO2 emissions actually from aviation. The sector is expected to grow actually quite significantly. So the synthetic aviation fuels are highly interesting. And this is synthetic kerosene at the end of the day, right? And so the synthesis pathways are typically done by Fischer-Tropsch right now, if they are synthesized. But certainly there are some drawbacks for Fischer-Tropsch. So what we actually study also at PSI, for example, is looking into scenarios how we can use different production pathways. So that would be sort of a route to do that, and it's basically a combined power to X, because you use hydrogen sort of in most of the cases, except you do a hydrothermal liquefaction and upgrading of biomass to produce the synthetic aviation fuels. But there are actually different options, and I would actually want to point on one option, which is still low TRL, but you can produce precursors for downstream synthesis in a very nice and efficient way, and that is the so-called co-electrolysis. Co-electrolysis is actually an electrolysis application where you electrolyze CO2 and water at the same time, and your product can be manifold, but the target product here would be carbon monoxide, right? And then this carbon monoxide you can use downstream in chemical industries to convert it into longer chain hydrocarbons, right? And this is a very interesting technology, and well, maybe the next slide I come back to this. First, I would like to mention the potential of aviation fuels, how they can actually reduce the climate impact. So one can actually reduce greenhouse gas emissions, net greenhouse gas emission, compared to fossil kerosene by up to 90%, right? So this is also a model, life cycle assessment model for different processes, power to liquid and sun to liquid processes. And so that is actually sort of the main message. You can go up to 90%. And if you additionally actually use during the production carbon capture, then you are almost at 100%. But there are always some small percentage which you are not able to decarbonize this way. Okay, so maybe the quick question on the co-electrolysis of CO2 in water. So what you do, you electrolyze CO2 together with water to produce carbon monoxide. And what we actually did, we were basically modeling a potential large-scale power plant, or planned how to produce that on different with different input parameters, also looking at different scenarios and different also electrolysis cell geometry. So there are a couple of proposals actually in the literature. So we, on the one hand side, we looked at the static product specific profit for two cases, a base case and a more sort of development case for what we expect to be or where we expect to be the technology like in 10 years. And even in the base case, one actually can already, for the CO production, one can already have a positive product-specific profit, right? So right now the technology is on TRL 4 or so, so technology readiness level 4. But even with this technology right now, one would be profitable. And the second thing is, if you look at the CO2 impact, actually for the base scenario, the best cell or best geometry of the electrolyzer in a plant, for CO production, you have just already negative CO2 emissions right now in the base scenario. With a more optimistic scenario, when we improve technology a little bit, one actually is a clear net zero, or can have a net zero technology, or a negative emission technology, to be more specific. So that would be one option, to produce CO through co-electrolysis and having a net zero technology. So summary and conclusions. Only 3 points. High level. Our net zero scenario is only possible when sufficient CO2 capture is implemented, when we electrify the different sectors, including transportation, and all of this electrification is also accepted, and Power to X is implemented to enable the flexibility and the seasonal storage. So these are sort of the 3 main things we need to achieve in order to become net zero by 2050. And with that, thanks to all the members of the division here, because many of the people contributed to what I have been showing here, and many thanks for your attention.
Okay, thank you very much, Thomas. And questions? Yes, please state your name before you.
Yep, Göran Eriksson from Swedish National Grid, the correspondence to Swiss Grid. I kind of lack something in your slides, and it's not only money that is needed, it's actually people working on the issues. So competent people, and so we lack a number of engineers in Sweden. I believe it's the same thing in Switzerland. Have you any comments to that? Are you stepping up? I mean, producing more engineers at ETH, or are you trying to reach out to young people?
Well, I mean, that's of course one of our goals at ETH, to produce people, or not, to educate people in topics of the energy transition. And actually, Switzerland did one thing by establishing, like in 2014, 8 of these Swiss competence centers of energy research. They were operating for 7 years. One of the targets of these competence centers was actually capacity buildup. That means educating people and creating people who stay in the energy sector and can answer the questions which are arising from the energy strategy. So beginning of 2021, this program ran out, so these centers are not existing anymore. And right now, at least, the people educated in these centers, about 50% of them remained in Switzerland, which is for sort of the international environment of the ETH domain we are in. That's a pretty good number, I think. Will they stay longer term? Certainly we don't know. But at least that was one of the attempts to answer exactly this question.
Thank you.
Yes, please.
Carl Kempe, can you explain why Switzerland is ruling out nuclear power? We are very sorry that a couple of years ago closed down 2 of our nuclear plants. Even if they were old, they could be renovated at a lower cost. But why are Switzerland ruling out? There's so much new technology coming into nuclear also.
I mean, the origin of this decision, and there was then also a public vote on it, so it's now also in the law. The origin of this decision was Fukushima incident, obviously. So that was the origin. So the acceptance was decreasing, and it was a political decision to phase out. So it's not, I mean, I need to mention the difference. You may know what happens in Germany. There was a clear date until, I don't know, 2022 or 20, I don't know exact year, we shut down nuclear power, period. That was the decision in Germany. The decision in Switzerland was we phase out. That means we are not building new plants. We are operating our existing plants until they are not economic anymore, they are deemed not secure anymore, etc. So Switzerland has had 5 reactors. One plant was shut down actually last year, I think. So it's 4 operating reactors. And the last most likely will go off grid between 2035 and 45. So that's a span, because it's not decided if one wants to have 50-year operation, 60-year operation, or even longer. So that's upon the regulatory authorities and certainly the operators, how much investment you need to do in order to keep it on a standard which is required. Right? So that was the decision. And yeah, I mean, the details why it was a political decision after Fukushima at the end.
Perhaps I can add something. I lived in Switzerland at that time when the referendum was, and I think it says in the law that they should not install any more reactors with current technology. That there could be new technologies coming. I mean, it's very flexible. What do you mean by current technology? And some people expressed it as the door is closed, but it's not locked. So that could be an option in the future. Yes, please.
William Dowler, University of Leuven, Belgium. I have 2 questions actually. A quick one, when you discuss electrolysis, you mentioned at some moment that oxygen is also a valuable product. For instance, certainly in the medical branch, etc. I have no idea in the industry or so. So when people usually make economic analyses of, let's say, power to hydrogen, and then keep going, if you were to include the market value of oxygen, how much does that differ in the results? Is that negligible, or does it make a difference of 10, 20%? I have no idea what the market value is of oxygen.
Probably I cannot give you a good answer to that. But comparing the scales, hydrogen is used and oxygen is used or needed in these scenarios. It's a marginal part. But it's still a valuable chemical. I mean, what we did during the pandemic, when we are operating a 100 kilowatt electrolyzer on our grounds, what we did, we used the oxygen during the pandemic actually and provided it to the gas suppliers because they were lacking oxygen because it was needed in the hospitals so much. So we just provided them the oxygen.
Because a very positive thing, of course, is it's very pure.
It's high, yeah, exactly. That's probably the purest oxygen you can buy. It's from electrolysis.
And if you allow me, and that's maybe because I didn't fully understand what you were doing, and maybe that's my fault. But no, when you discussed co-electrolysis, the route via CO is not very clear to me, because I always thought, well, CO, in the back of my mind, it's kind of, we don't want to have too much CO. We wanted to have CO2 because it's poisonous, CO, etc. But where does it come in? Why would you choose the route over CO versus CO2?
Well, you produce CO out of CO2 and water.
Okay.
Yeah, so reduce the CO2 to CO, so carbon monoxide. And carbon monoxide is a precursor. It's a typical precursor molecule. And basically hydrogen and carbon monoxide is syngas. If you can produce syngas in large quantities, you own the world, because with syngas downstream in chemical industries, you can do everything. I mean, except you need nitrogen. But in all the polymers and all these things, I mean, these are the precursors.
This proves that I'm not a chemical engineer.
And that is, I mean, just allow me one quick comment. I mean, that is actually a way to decarbonize chemical industries, by decarbonizing the precursors used in chemical industries. I mean, many people, many groups are working on specific processes from chemical industries and decarbonize them, which is feasible. But if you look at these integrated sites like BASF, for example, has in Ludwigshafen in Germany, I mean, it's all highly connected, and products from one plant or side products and so forth are going into another plant. So it's completely integrated. So if you just focus on one process, it doesn't help, because all the system around wouldn't work anymore. So you need to start, like in a Six Sigma process, you need to start in the beginning, right, and decarbonize the precursors, and then downstream you have much more decarbonized products. Yeah, so that's the idea.
Okay, 2 more questions first, up there.
Ja.
Yes, please.
Per Wickman Swan, KTH. So my question is about what are the main hindrances or like obstacles for this transformation? So I wonder, I mean, is it technical? Is it like scaling up the electrolysis, for example, or is it transportation systems, or is it political, or is it maybe investments? I mean, what stands in the way? For
I probably the right answer. It depends. So it's on the one hand side, from a engineering or scientific perspective, I would claim we have the technology, right? So the technology is proven for electrolysis, but also for other redox flow batteries and so forth. I mean, the technology is proven. The question is, on the one hand side, and that's probably differing from country to country or region to region, is the legal framework there, or the proper legal framework there, that investments can be taken, because the investments are from the private sector at the end of the day. In that industries need to invest, that's not us, right? And if the framework is not there, they hesitate to invest in scaling up technologies. And then certainly, I mean, these are underlying questions is, although the technology is there, do we have the the material resources to scale up the technology? I mean, one point, which I mean, for lithium batteries, why everybody tries to get rid of the cobalt, you know? Because cobalt used in the cathodes of a lithium battery, the cobalt is relatively scarce, very expensive, and also toxic. So we can build, right? I mean, a lot of batteries contain a lot of cobalt, but we want to get rid of it. The same in electrolysis. I mean, for the anode side in an electrolyzer, an acidic electrolyzer, you use iridium oxide as a catalyst. So iridium is one of the scarcest metals, if not the scarcest, on our planet. And it's a secondary metal. That means it is mined together with platinum and nickel. And the amount of mining is determined by the demand of the platinum and the nickel. Right? So if the iridium demand is increasing, there is not more production of it because it's coupled to another product. And the consequence is that the costs are going up. So these are questions we need to answer at the end. But technically, we would be able to do so, and it's then finally a political decision that we want to do it. I mean, I just met the R&D director from General Motors from the US, and he claimed a very similar thing. He said, technology-wise, we are there. It's a political and societal decision that we want to transition to use hydrogen. If we don't decide that, then we are doomed because we have a great technology, but it's not going to make it.
Okay, so, well, sorry, one more question. You were first and...
Olle Ingarnes, Linköping University. You probably answered my last question here because you told us about catalysts necessary to operate your electrolysis and the fuel cells, hardly scalable. But then I rephrase my question. What do you see as the possibilities of making scalable electrocatalysts for these purposes, going beyond the iridium, platinum, or whatever might be the choices of today?
So that is my personal perspective for water electrolysis. I think for the moment in a transition phase, we will be using PEM electrolyzers, so acidic electrolyzers, where we need to use iridium oxide. Currently, there's a huge effort in R&D in order to develop alkaline membrane electrolyzers. They combine the benefits of an alkaline electrolyzer with a polymer electrolyte membrane electrolyzer, which is acidic, because you have a very thin separator as a membrane and an OH minus and hydroxide conducting membrane. And so you can produce hydrogen with high pressures, which is important because hydrogen at 1 bar is useless. So you need to produce it with 50 bar or 100 bar, and that is what the PEM electrolyzer is actually doing. And they will be as efficient as a PEM electrolyzer, but the material requirements in an alkaline environment is not as stringent as it is in an acidic environment. So my perspective is, in 20 years from now, we will actually move into alkaline membrane electrolyzers.
Okay, so thank you very much. I think we have to stop there and go to the next presentation. So thank you very much.
Thank you.
Presentation.
So we have come to the third and last presentation of today, and the title is Future of Battery Technology, and it will be given by Professor Daniel Brandell from Uppsala University. Sorry. Daniel Brandell is a professor of materials chemistry at Uppsala University, where he manages the Ångström Advanced Battery Center. He has been active in battery research for more than 20 years. He holds an ERC Consolidator grant on polymer electrolytes. He also coordinates Battery Sweden and is part of the Swedish Electromobility Center. So please.
Tack. So it's nice to be here, representing the local research community and the Swedish one, and I try to give a little bit of a Swedish perspective also on the future of battery technology and where this field is going right now. As I have already been introduced, my name is Daniel Brandell. I'm actually substituting today also for Kristina Edström, that some of you may know very well, that I work very closely with at Uppsala University. I will start with what is currently happening in battery industry in Europe. This is data from the Fraunhofer Institute, and it's a little bit older data, so I think this is from 2020, yes, October 2020, and this is the lithium-ion battery production in Europe. And what we can see is that we had virtually no lithium-ion battery production in Europe just a couple of years ago. Now we see that we are on the rise. A lot of things are being built, and it's a very rapid development. These different colors on the bars, they represent different initiatives, different sort of gigafactories that are being constructed around. And what we can see, and this particularly may be interesting for us, is the gray bar on the bottom that represents the Swedish initiative Northvolt. This growth is very much correlated with the growth of the electric vehicle sector. Lithium-ion batteries are implemented for other purposes. I mean, traditionally, 10 years ago or 5 years ago even, the dominating market was mobile electronics, computers, cell phones, etc. Now batteries is the major vehicle batteries is the major market, and this is also what we expect will grow. Stationary storage, as was mentioned, is interesting for lithium-ion batteries for some part of the load leveling and the stationary storage solutions, but it will be a minor market segment until at least 2030. We can also see that lithium-ion batteries are outgrowing the other mature battery chemistries. If you look at the battery industry, just a couple of years ago, it was still dominated. The major product was lead-acid batteries. Now lithium ion is what is growing, and this is also what is seen from the statistics. And this is of course due to performance. It's a battery with a very high energy density and a very long lifetime as compared to many of the options, but with some challenges that I will also address. This is a more recent picture actually on the European landscape, and this is the geography of the battery factories being built around Europe. We can see that very many initiatives are taken. This is a geographically very diverse picture. Eastern Europe not so well represented, but clearly Northern Europe, Western Europe and Central Europe have gigafactories being built. And this is also very difficult to keep up to date. This is a couple of months old from CIC Energy Gune in Spain, and it's already outdated because we know about other initiatives that have been started up. We can also see that some of these companies are traditional European actors on the scene, like Varta. We see newcomers like Northvolt. We see the big Asian battery manufacturers, CATL for example, LG and Samsung are also building in Europe. And we also see quite a lot of active factories being built by vehicle manufacturers that are now starting also to produce batteries, like Tesla or Volkswagen. I think you might have heard about this concept about the Nordic battery belt. Sometimes this was illustrated as a rather narrow belt, just in the very northern tip of Sweden, Norway and Finland. Actually, considering now that we have gigafactories being built and planned also in other parts of Sweden, Gothenburg area for example, we need to stretch this belt. This is a rather attractive place actually to fabricate battery cells if you look at it from what you need in order to build a gigafactory. Salaries are high in the Nordic countries, but we have quite a lot of other appealing things. We have a very robust energy system, and it's very affordable energy by comparison to a large part of other places in Europe. We have a lot of minerals, especially on the Finnish side of the Baltic Sea, and synthetic materials being produced in large volumes in Norway. We have a very early start of the battery production as compared to many other European countries. One could say that Northvolt has given Sweden actually quite a head start in battery production on the European scene. And we also have a lot of knowledge and competence. Not enough to supply the sector with what is needed, but we have actually a good foundation that we have had research and education within the battery sector for decades in this part of Europe. And considering this, we can take a look at the battery value chain. So if we look at the battery value chain, we can start here with well, this was difficult, but the raw materials that we have down on in the left corner. This is where we have mining and extractions. This is what we then use to produce advanced materials, processed materials. We then go with these materials to the battery production and manufacture cells, modules and battery packs. And this also needs a lot of other equipment in order for the battery to function well. We need control and monitoring and also modeling of these battery packs. So it becomes an integrated system that is then being utilized by the batteries in usage for a fairly long lifetime. And then afterwards it goes to recycling. Lithium-ion battery technology, it's a fairly mature technology. It has been around since 1990. And it means that a lot of the different materials and the different concepts has been already researched quite heavily. There are certainly tens of thousands of battery publications being present in scientific literature. No one has read everything. The major questions that we are asking ourselves right now and that will become the center of attention in upcoming years is really the interplay between different parts of the battery value chain. How will the raw materials be controlling how we can make the battery in the battery production in the actual factories, and how will this eventually turn out on how the batteries will age, and how will this also determine how we can recycle the batteries and to what rate we can recycle them. This is areas, the interplay between these different parts of the value chains that are largely unresearched today, and where we need to make a lot of scientific development. If you look at research and education, it's needed throughout the entire value chain. We need to have people educated that understands all parts of this life cycle or this circular economy. And if we look at the battery research field as it has been until today, if we look at battery literature, for example, it's really in the segment of advanced materials where we have the core of what has been scrutinized. We have also quite a lot of, and this has then been controlled by people that has a background in material science, materials chemistry, electrochemistry. These are the people that have dominated this scientific field. It's also the core of our research group in Uppsala. Then we have had some electrical engineers, talented people that have worked quite a lot with battery usage, how to implement this into a vehicle or in a storage product, and understanding this from much more from an electrical engineering point of view. But if we're gonna scale this up and electrify the entire society, we need a lot more people coming into this area that has completely different types of background. We need people from geoscience that knows raw materials and the raw material sector. We need more people that understands processing, how to process chemistry, both for the battery fabrication and also from the battery recycling perspective. We need also people that comes in from IT, that understands control, monitoring, modeling. We also most likely need people from business economy that understands different of business model in order for implementing, for example, the battery to grid solutions that the previous speaker mentioned. So this is an area where we need to step up and actually expanding through the value chain, while we also need to develop much better materials and also understand the interplay between these parts of the battery value chain. If you look at the battery research and the core activities for cell chemistries, this is such a diverse area, and it's also because a battery cell is such a diverse and complex component. One way of sort of dividing this into different parts of the battery research area is to look at the different battery components. You can clearly see that there is a lot of people that consider themselves occupied, or they are preoccupied with developing new anode materials or understanding anode materials or cathode materials for that matter. We have people that are experts on liquid electrolytes, on solid electrolytes, people that are completely focused on developing separators, different type of binder system for the electrodes. Cell-feeling component is a very rapidly expanding area, very much on tailoring the interfaces in the batteries. Another way of looking at this is this research field is also to divide it into different type of battery concepts that have been studied. There are still a lot of interest in the research community when it comes to lithium-ion batteries, particularly when it comes to safety, very rapidly growing research area. Also understanding battery aging, where a lot of the sustainability gains can also be made if you can prolong the lifetime of the battery packs. Then there is also a lot of research on other type of battery concepts right now. A lot on the solid state chemistries, both with the ceramic electrolytes and the polymer electrolytes. I will mention a little bit more about that later. A lot of research being carried out on sodium-based batteries, and then on other type of metals, zinc, calcium, magnesium, potassium. Research is being carried out heavily also on dual ion concepts, on organic batteries, redox flow cells, lithium sulfur, metal oxygen. And then the third way of looking at the research landscape is also to look at all the method-oriented development that are currently being carried out. A lot of structure characterization and surface characterization, a lot of using neutron sources and synchrotron sources in order to analyze and understanding battery phenomena. Online characterization is growing rapidly. Implementation of new sensors and types of sensors into batteries, and also the development of electroanalytical techniques that can be easily then transferred to the battery management system. Very large efforts into modeling and also into AI methods and implementing this. And of course, individual battery research are preoccupied either with different type of components, implemented into different concepts, and then also with people that are method experts. This spans a very large research landscape, from the material side to the different cell chemistry side to the different methods, and where we are at interplay with each other. If we are going to compete in the net, if you're a small player. If you look at the Swedish landscape when it comes to industry and also to research, we actually have what I would consider a rather good starting point in this country. We can look at, for example, this competence center, Battery Sweden, that is the center focused on research and development and that gathers academia and industry in Sweden. If you look at the partner there, we have 3 different universities, Uppsala, Chalmers and KTH, long-term players in the battery research area, have a history of publishing battery research articles on lithium-ion technology or lithium metal technology since the early 1980s. We have RISE Institute of Sweden, also has a lot of competence when it comes to process engineering and different type of analytical techniques. And then a range of companies that actually covers the entire value chain. Companies from the raw material sector, the recycling sector, the vehicle sector is of course important in a country like Sweden, component developers, cell developers for both lithium-ion and sodium-ion. And this is actually quite an attractive starting point for Sweden to take a step forward and to actually become a very major player and within the Nordic battery belt and within the European Sea. We also have a stronghold also by our efforts in the European battery landscape. Uppsala University, for example, is coordinating Battery 2030 Plus, which is this great initiatives by the Commission to make Europe world leading in batteries. So we have something to build upon, but we need to be more people and adding on more competences. So in order to discuss the technical challenges a little bit better, we need of course to study what is in the lithium-ion battery cell. And this is also necessary to understand in order to understand why we would like to develop the lithium-ion battery further. So the battery consists of 2 different components, the anode and the cathode. The anode is extremely reactive, and the cathode is also extremely reactive. But they are reactive in different sense. One would like to give away electrons, and the other one would like to accept electrons. It is the difference between these 2 types of reactivities that controls the battery voltage. Then the number of times that the reaction can take place, that is equivalent to the capacity. And the capacity multiplied with the voltage becomes the energy. Apart from the anode and cathode, we also need a number of other things for the lithium-ion battery to function. In between these 2 components, we need to have a separator. Otherwise, we will have an internal short circuit and the components would react with each other. Then on the back side of both electrodes, we have 2 current collectors, copper and aluminum. Copper is problematic. It drives up the price. It's a rather scarce and expensive element, and it's also a little bit heavy, which then controls a lot of the final weight of the system. Both electrodes are porous in a lithium-ion battery. So they are particles of the active materials that are held together with a polymeric binder. And in these pores, they are filled with a liquid electrolyte. It's the same thing on the cathode side, where you also need to have a lot of an additional component, that is the carbon black, because the cathode is normally a very poor electronic conductor. The binder, the carbon black, the electrolyte, the separator, the current collectors, they are the dead weight of the battery. The active material is only in the active material, cathode and anode. If we look at the anode first, we have a number of different choices. The traditional choice of material is lithium integrated into graphite. In between the graphene sheets of graphite, we can store lithium. And when lithium is inserted there, it becomes very reactive towards and would like to oxidize. Graphite is somewhat problematic. It contributes quite a lot with the battery aging, and the energy density is not exceptionally good, which means that today there is quite a lot of silicon graphite composites being developed, where you implement more and more silicon into the graphite. You also have alternative materials that are much more robust, for example, lithium titanate oxide, that is down in the left corners. And then you can utilize a whole range of different binders. Now the recent technology has been the technology development has gone towards cellulose-based binders and things that you can use for the water-based processing. Separators are often different sheets of polyethylene, polypropylene, ultra-porous materials that are pressed on top of each other, synthesized very elegantly, and produce a porous matrix. Also here you can use other type of materials as long as they are chemically and electrochemically fairly inert, and also electronic insulators. On the cathode side is where you have the most diversity. We have different forms of cathode materials in a lithium-ion battery, and this means also that a lithium-ion battery is not really very uniform. We have very many different types of lithium-ion battery. It's often controlled by the cathode chemistry. The most utilized today are the layered oxides that we see on top. Lithium cobalt oxide is the standard material, often used in cell phones and portable electronics. Now, as we have heard, there is a drive towards replacing cobalt as much as possible because it's expensive, it's toxic, it's a conflict mineral, and it's being replaced more and more to a small fraction with manganese, but largely with nickel. And this also actually increases the energy density. There is something good with this. At the same time, it makes the material much more reactive, which means that it's difficult to stabilize it for the lifetime we want in the battery. An alternative family of cathodes is the polyionic compounds, where especially LFP is very, very interesting. Gives a little bit of a lower voltage in the battery, but that also has good effects because with that it becomes less reactive, and that means that you have less side reactions. It's also very robust technology. It also contains none of these very sensitive and delicate and exotic, one might say, transition metals. It's based on iron as the active component. And this is, of course, also attractive from a cost and sustainability perspective. But you lose some energy density, roughly 20% at cell level, if you're switching from lithium cobalt oxide to lithium iron phosphate. And for many applications, this is too much of a trade-off, especially for the vehicle industry. But then again, Tesla will also produce a line of cars that are operating with lithium iron phosphate as the active material on the cathode side. since batteries are all the way becoming better and better a little bit by good engineering and good materials chemistry, maybe you can lose some of the energy density and compensate with having something that is much more sustainable and much less costly. Another way of reaching cobalt-free chemistries is to look at the spinel structures. Lithium manganese oxide was heavily researched in the 1990s and beginning of this century. Not stable enough for long-term operation. Now there is a lot of interest in another type of spinel, that is lithium nickel manganese oxide, also has large stability problems but show a lot more promises. It's a lot of the major manufacturers are looking into this as well. It has a very high operating potential, which makes it very prone to side reaction. But with a very high manganese content, it can also be a very good compromise when it comes to price. On the cathode side, you often stick with using these very fluorinated binders, PDF, for example, just in order to have something that is very chemically inert and not as prone to side reactions at these high potentials. Those were the active materials and a little bit of the binders in the electrodes. Then we come to the perhaps most complicated thing that you have in a lithium-ion battery, and this is the electrolyte. Every electrolyte, we are close now to the Arrhenius lab, named after Arrhenius, who was the very founder of the electrolyte field. Electrolytes are composed by a salt and a solvent, and water is in most cases not a very good solvent to use in any type of lithium-based battery chemistries, just because you will have the effect as you have in an electrolyzer. It will spontaneously react in an electrochemical reaction and produce hydrogen and oxygen. So instead you use organic solvents. These are more stable than water, but they are not completely stable. They are very prone to side reaction. It is controlling the side reactions of the solvents that is really the key to getting the lithium-ion battery to work. This is actually what was one of the major inventions that actually led to the commercialization of the lithium-ion batteries in 1990. And also one of the people that received a Nobel Prize for this achievement a couple of years ago. The salt that is in use in almost all lithium-ion batteries is lithium hexafluorophosphate. It's a complicated salt, but it's good with these solvents in that it renders a very high conductivity. At the same time, it's also prone to a little bit of side reactions that are very useful for passivating other components in the battery, not least aluminum, which is prevented then from aluminum corrosion. And then what makes it even more complicated is a vast range of additives that are used in the battery electrolytes. For example, FEC that we see here, but we have film formers, you have redox shuttles, you have water scavengers, a lot of different side components. A commercial electrolyte usually have 20 to 30 different components, and this is of course super secret and it's very painful for us academic researchers who are trying to analyze commercial battery cells if we don't know what is in there from the beginning. A couple of major challenges. Lithium hexafluorophosphate, or the hexafluorophosphate anion, is super sensitive to water. Just trace amount of waters, ppm levels, will lead to side reactions. And that produces hydrogen fluoride, which is corrosive and can attack other components in the battery cell. What is even more problematic, if we have a battery accident and the battery is exposed to air, then we have HF coming out of the battery. And HF has a toxicity problem that is not so nice. The organic solvents are very flammable, especially dimethyl carbonate and also diethyl carbonate. Has low vapor pressure and makes the fires that can start from a side reaction make the fire spread very rapidly. It's difficult to extinguish. Battery toxicity, battery safety has not really been that well researched, but considering the volumes, the sheer volumes of production and implementation into the energy system, is becoming quite vibrant research fields. So a little bit of the forecast and the roadmap ahead. We will see a combined evolutionary development, combined then with a couple of revolutionary leaps, is at least what we hope for, that are researching this area and have hopes for this technology. So in the very short perspective, we will see this gradual evolution of the lithium-ion battery. The energy density of the lithium-ion battery has increased a little bit linearly since its market introduction in 1990. And we foresee this to continue to increase to some degree. It's around a couple of % per year that we get by implementing novel electrode materials, and perhaps primarily, but very smart engineering of the battery cells and the packs and the modules. What is happening now on the anode side is what I mentioned. There is a lot more implementation of silicon. If we have 20% silicon together combined with the graphite, we have roughly 21% increase in energy density, theoretically. And this is, of course, very good and useful, but silicon has a much more complex chemistry than graphite when it is being alloyed with lithium. The surface chemistry is very difficult to monitor, and the bulk chemistry is equally difficult to monitor. You lose a lot of lithium in these. Good, thank you. On the cathode side, we see another type of development with more and more nickel-rich materials, where we also see a similar increase in density. We're also seeing, as I also mentioned, a development or a wish to create cobalt-free cathodes. Then we have one of these revolutionary jumps that we are hoping for, the lithium metal chemistries. And lithium metal is very reactive with liquid electrolyte. This is problematic, super problematic control, because what happens in liquid electrolytes is that we grow these needle-like structures with lithium that is forming as dendrites, and they can penetrate the cell. Leads to a lot of different side reactions and also to safety problems. But with different type of solid electrolytes, we can mitigate this problem and implementing lithium metal. Then we foresee also another revolutionary jump with the implementation of new battery chemistries, lithium sulfur, lithium oxygen, organic electrode materials, and primarily, perhaps in the short term at least, sodium-ion batteries. And if we look then at the landscape for this is these different chemistries that are plotted in a diagram that shows their energy density. So we have on the y-axis, we have the gravimetric energy densities for different battery chemistries. And on the x-axis, we have the volumetric energy densities. We see lithium-ion is fairly well placed there in the middle. We see sodium-ion is a little bit of a compromise in terms of energy density, but much more sustainable. No lithium, you can use cobalt-free chemistries rather easily. You can use aluminum instead of copper as the carbon collectors. Solid state, what we are hoping for, the next generation, is up here. But having such a high energy density battery also puts a lot of challenges in order to mitigate all the side reactions that might be involved. And this is just a theoretical energy density. There are a few take-home messages from this slide. First of all, there's quite a striking difference for some chemistries. Look at organic batteries and lithium sulfur, for example, when it comes to volumetric and gravimetric energy density. They are really high in gravimetric energy density. But gravimetric energy density is not always the most crucial thing to have. For a vehicle, for example, volumetric energy density, if it's a passenger vehicle, is much more of a metric of choice. This means that these batteries, although they have a very high appealing energy density or specific capacity, are not as useful for these type of products. At the same time, you can look at aluminum chemistries that are equally good as lithium in terms of volumetric energy density. The second take-home message is that it's very easy for people to focus only on the energy density. But this is not the only relevant parameter. And this is also why some of these have very little future, at least from what the battery research community is thinking currently. Because they lose in cyclability, in efficiency, in safety, in cost, in sustainability, in power, in charging time, etc., etc. And these are why these alternative battery chemistries are not mature technologies enough. One of the selling points for batteries is the energy efficiency. This is a comparison for passenger vehicles between a battery vehicle, hydrogen fuel cell vehicle, and one based on synthetic fuels. The energy efficiency in batteries for this kind of system is very, very high. You lose a lot of the energy in the conversion to hydrogen and a lot in the conversion back to electricity. Even higher losses when it comes to synthetic fuels. At the same time, batteries are, and that we heard from the previous speakers, not as versatile. So for a lot of things that we need energy storage for, batteries, or lithium-ion batteries in particular, are not that ideal. There is a lot of challenges. We need a much less costly alternatives, especially for small-scale storage of energies. Lithium-ion is, we've seen a downfall in prices, but we expect the prices to increase, and they have actually started to increase just the last couple of months. For transportation, and that was also pointed out by the previous speaker, passenger vehicles, lithium-ion batteries are excellent, but when it comes to heavy transport and aviation, marine transport, energy density is just not sufficient for most of these solutions, apart from niche applications. For the grid, we need much more scalable solution than what we can most likely do with the lithium-ion technology. But redox flow, for example, other type of battery chemistries could well serve us here. How much time do I have? 0 minutes. Okay.
Okay.
I just wanted to say something about then, the availability of material, since this was addressed previously. Lithium is maybe most of the materials that we need for fabricating lithium-ion batteries. We don't excavate them enough in Europe. The main producers are outside of Europe. Especially cobalt is very problematic. Lithium, there is plenty of lithium. It's just that it's very cheap to import it from South America. Recycling, we need to increase also there quite a lot. But here we have something that we can do in Europe. What is looking very alarming right now is not actually these that traditionally has been pinpointed, like lithium or like cobalt, but nickel prices that are skyrocketing right now due to the conflict in Ukraine. Russia is a major exporter of nickel to Europe. And we have no idea where this development will take us, at the same time as we implement more and more nickel into the batteries that we are fabricating to a larger and larger extent. I had some conclusions that I think I will skip because I've already mentioned most of this, and instead leave room for some discussion. Thank you.
So we are a little behind schedule, but it's very interesting, so I think we can stay on and take a few more questions. So, please. Yes?
Excuse me. The battery in my car seems to get lazy after 5 or 10 years. How long will these battery storage systems last? How long can we expect them to be?
Yeah, the batteries that comes to the market today, I guess if you have a battery vehicle or a hybrid, maybe it has a few years. The batteries today are actually much better than the generations that were produced at least 5 years ago. It's very few batteries, vehicle batteries, that goes into recycling today because they are still outperforming the old warranties. It used to be maybe a 7-year warranty for a battery pack, but most of these batteries have actually outperformed all expectations. The generations that are implemented into battery electric vehicles and hybrids today, we foresee that they will live much more than 10-15 years. The vehicle producers themselves have a very strong belief in the current technology.
Please.
Yes, we have, as I see, two developments. One is a high density for cars and then the low density for long-time storage and fixed installations. What do you think the development will be there?
I think you're completely right. This is what we will see. We will see different type of energy storage solutions implemented into different segments of the energy systems, where right now it has been lithium-ion implemented everywhere. But this is actually a waste of some of the very scarce materials that we have, and it's not economically feasible, and actually it's not really that ideal either. What we need to think about when we are implementing these energy technologies that are low in energy density is that for every cell that you produce, if we're talking about batteries, you also need to have a lot of cables and wires and systems and maintenance, etc., etc. A low energy density, if the cell has too low energy density, then it will still not be really economically viable or sustainable in that matter, just because all these other system demands too much. We can compromise in energy density, but maybe we cannot compromise that much.
I would like to continue on that, and also with regard to when you showed the volumetric and then the mass density, where you had there two on the left-hand upper side, yeah, those two. And you said, okay, when this is for transport, that is a problem. Okay, you have high mass density but very low volumetric density. But if you're talking about long haul,
yeah,
where you have more room,
yeah,
isn't it that that's what I read these days, that
yeah,
it's getting gradually that also batteries are coming into play more and more also for long haul, intermediate long haul transport, and not for the very long haul, of course, but
no.
Is that right? Or
yes, it's right. Lithium sulfur, for example, could be actually sustainable for heavy-duty transport. It's also been something that people have looked into when it comes to aviation. I think that maybe there can be a niche segment of aviation where it can actually play a role. But when it comes to long-term aviation and large passenger vehicles, then you need synthetic fuels or hydrogen. This is also what the aviation industry think themselves. And I think the energy density here is still not sufficient enough. Even if you build an entire plane in lithium sulfur batteries, it will still not fly that far.
Okay. One more quickly.
Yeah.
Okay. In the 90s, one of the magic words for lithium-ion batteries, but I'm not an expert in that, there was Nafion.
Yeah.
You didn't mention it at all. Is that something that is from the long, long past ago?
Nafion is a very nice fuel cell membrane, also used in electrolyzers, etc. You could use it as a separator also in batteries, and some people have played around with this because it's also very useful for redox flow batteries, for example, where you need an ion exchange membrane. It's a rather expensive material. It has poor sustainability, and it's for some niche applications, it can actually be quite useful, especially when you consider lithium metal. If you want to combine it with a liquid electrolyte, maybe Nafion can actually be good in order to prevent different type of side reactions.
Okay. Sorry.
So, Thomas.
So this is more like a comment on one of your last slides when you compared the round trip or well-to-wheel efficiencies. Of course, that is absolutely correct what you're showing here, but there's the but. I tend to show also, if if numbers are available, in a battery, your fuel is internal. So basically, it's the electrode material, active materials, and you need to produce them too.
Yeah.
So in this comparison is actually not 100% fair in a way, because you include for power to liquid and power to in hydrogen, you include the fuel production.
Yeah.
Whereas in the battery you don't. So actually the overall efficiencies you're showing here are actually not a fair comparison from this perspective.
But if you would include that, then you also need to put into also the cost for the fuel cell, for example. And also,
well, it's not about cost, it's about energy losses,
I mean,
right?
what you're thinking about with the battery is that you have a material, you charge, discharge, it has a lifetime of 10, 15 years, maybe longer actually than most of the fuel cells. I agree that this is biased. It's a very, very rough simplification, but at the same time, it's very difficult to make something that is super transparent.
Right. I completely agree. I completely agree. But I mean, it's a little bit misleading.
It's a little bit misleading. I agree.
Yeah.
You need a footnote.
Yeah.
I think we can take one more question. If not, I'll put that question. And you talked about all the competencies you need here from different disciplines, engineering, material science, and so on. And I think you expressed that you are quite confident that you could get that competence. But is there a bottleneck in these competencies? Which is the most critical that you are facing today?
The most critical thing that we are facing today is actually that we don't really have a kind of commitment within the educational system that we can educate all of these people that we would like to educate. We lose a lot of competence in this country right now. I mean, we have people leaving, battery experts that are leaving the country right now because they cannot find a solid position within academia, although they are very good. And if we are going to increase and educate 1,000 battery competent engineers per year, if I go to my university and ask and tell them, we can do our fair share in Uppsala, we can educate 200, then they would say from the university management that, okay, then we need to educate less doctors or less people in law. Because there is a cap on this. So we need something that is much more of an incitament for us to recruit teachers and to scale up education. We cannot do this by ourselves. We need much stronger incentives from the political bodies.
And I think it does not only apply to the battery sector, but
no,
every other sectors in the energy transition. We need good skilled people that can deal in the end. So I think we have to stop there. Thank you very much once more for your presentation. We have
come to the end, and I will just once more thank all the presenters for coming here. I think it has been the most interesting morning here. I have learned a lot, and I hope that you also have got new insights in this topic. And we have seen that this is very complicated and complex issues here, so there is no single answer. You have to go into the footnotes, as you say, to see when you look at these comparisons. So thank you, and also you here in the audience for coming here today. And I will also remind you that we have the third seminar in this series will be on the 7th of September, I think, which will be on energy efficiency. So if you not have already registered for that seminar, so please do it then. So thank you very much. And now there will be a sandwich lunch, I think, waiting for us outside the room. So thank you very much for coming. Thank you.